Alright, hello guys. So this final lecture I'm going to be addressing a few of the questions that I received. Those topics include correlation, the interaction term, prediction / confidence intervals, and the assumptions. Okay, and all of these are related to the linear regression. So within 2 examples, I should be able to cover all of these topics. All right, so I sent you this corona data set, and so we need to read that in. Using our standard method. Okay. So looking at my data set, we've got 2 variables, days and new cases. Okay. And so I want to attach my data. Okay. And so first thing I might want is a scatter plot of x. Yep, x is going to be days, and new cases is going to be y. Okay, so what we have here is basically days out since the start of the virus. Okay, and what we can think of y here as being some sort of a measure of the number of new cases that we're seeing. Okay, so to some scale. Okay, so we can see as the number of days go out, right, where we start seeing fewer and fewer new cases. Okay. So to address the first topic, which was correlation, we can simply put correlation x comma y, and we can see that we get negative 0.73. Okay, so in this case, r is equal to negative, which is very important, 0.73. Okay, so we have a strong negative linear relationship between the number of days and the number of new cases. Okay, so as we increase the number of days, we start seeing fewer cases, right? Because it's a negative relationship. Okay, the strong, if you remember, I gave you a rough subjective scale that said basically, 0.6, 0.7 above that is going to be strong, either toward 1 or toward -1, right? And this is negative. So the only difference is that we have the word negative here instead of positive. If this was a positive 0.73, then we would just have a strong positive relationship in the scatter plot instead of looking like this, or basically we can clearly see we have a curve here. Instead of looking like a downtrend, it would look like an uptrend of some kind, okay? And then again, strong, right, it's because it's fairly high, 0.7 to 1, say, or negative 0.7 and -1. Okay, again, we might have moderate, say, between 0.4 and 0.7, or negative 0.4 and negative 0.7, and then between about negative 0.4 and positive 0.4, right, the range closest to 0, we might call that mild, okay, or weak. And of course, correlation is specifically relating the linear relationship, okay, so basically straight line relationship. Okay, so we can see it's actually still fairly strong, even though we can clearly see that there's a quadratic relationship going on here. So the correlation is negative, right, and it's fairly strong, but that doesn't necessarily mean that the linear relationship is the correct one, okay? It just says that if we were to look at this as a linear relationship, they still do have a fairly strong negative linear relationship, even though a quadratic relationship would be even stronger, right? Okay, so that's really all there is to correlation, okay? And I'll probably only ask you about correlation in a simple linear regression model like this, where we have two variables, an x and a y, and basically I ask you to calculate and interpret the correlation between the two variables. Again, if we had some sort of increasing pattern, whatever that might look like, then the correlation would be positive. If we have kind of a straight line, the correlation is probably going to be close to 0. Okay. And it is possible, like if we have some sort of a, say, decreasing and then increasing pattern, we might also have a correlation of 0. Right? If this, instead of just continuing to go down, if this went all the way back up, then we would have a correlation of close to 0. Okay, because that's basically perfectly against linear, right? Just thinking about if this was a complete U of data points, right? Trying to fit the best possible straight line through that would basically be a flat line, which again has slope of 0, correlation of 0. Okay. I did try to mention before that slope is somewhat related to correlation, but not perfectly related, such that if we have a slope of 0, we have a correlation of 0. If we have a positive slope, we have a positive correlation, and if we have a negative slope, we have a negative correlation. But if you take two sets of points, okay, and the only thing you do is change them by shifting them up or down, basically changing the slope a little bit up or down, that doesn't change the correlation, okay? It's the correlation is basically measuring how tightly the set of points falls about a straight line. So if you just think about taking a set of points and just shifting them a little bit, like just even take this curve and just think about taking the entire plot here and just shifting it a little bit, right? Such that the points are in the exact same pattern, they're just shifted a little bit. The correlation would still be the same. Okay, because the scattering of the points would be the same. Okay. So we might want to do our linear regression here. So go to my ANOVA regression code. We've already attached our data set. We don't want ANOVA. So we might want to create our regression model. And so we have y is the number of new cases, new dot cases, and x is the number of days. So we can do this. And so we can see our fitted regression model is y hat is equal to 2.6 minus 0.01 times x, right? And putting that in terms of what we're talking about, right? The number of new cases is equal to 2.6 minus 0.01 times the number of days. Okay? So if we put in a number of days, then basically we get a measure of the number of new cases of the coronavirus that we should be seeing. Again, just to some scale, right? It's just kind of a constructed data set to some scale, okay? And so I might as well just go through the whole thing here, interpreting these things. So basically, interpreting the y-intercept. So basically at day 0, right, we expect 2.6 new cases. Okay. So I guess you could think about this as kind of at the very start of the spread of the virus, we expect 2.6 new cases. And of course, right, units, they're just some units that might make sense. Okay, 2.6, right, 1,000, etc., whatever, new cases. And again, this is at x is equal to 0, right, at day 0. Okay, enter. And so that actually might make sense in this case. So the slope is 1 in simple linear regression. That should always make sense, okay? And so for every 1 unit increase in x, so every 1 additional day, we expect y, the number of new cases, to decrease, right, negative, decrease by 0.01. And again, write units. We don't have units. So for every one additional day, we expect the number of new cases to decrease by 0.01 units, right? So as time goes on, we expect the number of new cases to decrease. Okay? So what else might we want to do? Right, of course, MSE, if you just put ANOVA, ANOVA and a reg dot model, right here, the residual mean square, or error mean square, MSE, right, so about 0.41 is our unbiased estimator for that common error variance, sigma squared. Okay. What else do we have? We might want confidence intervals. Right here, I'm specifying a 92% confidence interval, but put whatever you want. Okay. So here's for the intercept, and just going ahead and looking at the slope, right? Basically the same thing as this, but we're talking about an interval, right? So for every one additional day, here, I'll just go ahead and put it. So this is our confidence interval. So we are 92% confident that for every one additional day, we expect the number of new cases to decrease by between 0.0, I'll just shouldn't round, 0.0, round it like that, 0.019 and 0.01, okay? And of course you could flip those if you wanted. But because it's negative, we have to put our decrease, right? So we expect the number of new cases to decrease between about 0.01 and about 0.02, right? So fairly standard, right, how we always kind of interpreted things, but we do have to put it in this special context of what it means, what the slope means, okay? And same thing for the intercept, right? You can do the same thing for that. Okay, so another of the questions was about prediction and confidence intervals. Okay, so first I'll just go ahead and do a confidence interval and level. I'll just go ahead and do a 95% confidence interval. And so one question we might have is, say at 3 months out, right, 90 days, 3 months out, what do we expect the average number of new cases to be? Okay, what do we expect the mean value of y to be? Okay, that, if we're interested in the mean value of y, that would be a confidence interval. Okay, so what we could do is, right, this is what we need to replace this x here. This is our x value. So we would need to put days is equal to 90. Okay, because we want our x to be 90. Okay, and we're doing a confidence interval. So we are 95% confident that right after 3 months at day 90, the average number of new cases will be between 1 point, I just put 1, it's close enough, and 1.8. Okay. Oh, we'll do the prediction interval and then I'll try to explain the difference. Okay, so now what we might want to do is do a prediction interval. Okay, so if we're doing the same thing at day 90, the only thing we have to do is change comp to pred. And we get this. So if you remember, prediction interval is actually probability. So there's a 95% chance, I'll put it like that at day 90, the number of new cases will be between 0.02 and 2.8. Okay, so I guess to make this make sense, right, we have multiple data points here. What these might be is for, say, random or for large cities, say, right? We've different large cities. We're kind of seeing the number of new cases, okay, and at different time intervals. So when we think about the average, right, thinking about just averaging over like basically everyone, right, over all the large cities, then we expect on average the number of new cases to be between 1 and 1.8. Whereas what a prediction interval is saying is it's not averaging over all of the y values, right, for a specific x. What it's saying is if we just pick out a single y. So basically, instead of saying averaging over all new cases, kind of averaging over all the cities, if we kind of randomly select a city, kind of, okay? So if we randomly select a city, then there's a 95% chance that at day 90, the number of new cases will be between 0.02 and 2.8. Okay, so that's the main difference between a confidence interval and a prediction interval for, of course, what we're specifically talking about is a confidence interval for the average value of y for a specific value of x, right? That's what we're comparing, confidence interval for the average value of y for a specific value of x versus a prediction interval for a random value of y for a given x, okay? So prediction interval, we're predicting y for a single x value. Confidence interval, we're predicting the average value of y for a single value of x, okay? And so confidence interval, because technically an average is a parameter, right? It's some true value. Whereas prediction interval, we're just picking out some future observation, which is why it's probability, okay? Because it is a future event, basically. Whereas an average is something kind of set in stone. We just don't know what it is. Okay. So confidence intervals for the mean of y at a given value of x, prediction interval for a random value of y, again for a given value of x. Okay. All right. What about summary? Okay, summary reg.model. We can see that go ahead and assume alpha is 0.05, and which you should assume unless I specifically tell you otherwise, which I may or may not. And so our p-value for our x, our number of days, well, not for x, for beta 1, which relates x to y, right? So the p-value for beta 1 is small, smaller than 0.05. Thus, we reject the null that beta 1 is equal to 0. So we have evidence that it's not equal to 0, right? So again, small p-value, we have evidence that x is related to y. So we keep it in the model. Okay? Interpreting r squared, right? Our model, which is basically just the number of days out, accounts for a little over half of the variability in the number of new cases, right? So basically just thinking about it like this. If you tell me how many days out we are from the kind of the inception of the virus, then I basically know about half of the information that there is on how many new cases there are going to be, right? So I still know a lot, right? But there's certainly a lot that number of days doesn't account for, right? For example, the number of new cases, you can just think about it like this. The number of new cases is probably going to be varying, right? For a large city versus a small town, right? Whether it's a poor country versus a more well-to-do country, right? So there are certainly plenty of other factors other than simply the number of days out we are that is going to determine how many new cases we're seeing, right? Okay, so um, of course I'll leave that for the next example, I think. Um, so one thing we haven't done, right? We have not checked our assumptions yet. Got to check our assumptions. Okay, so let's see what the assumptions look like, right? Oops. So plot reg.model, right? We're going to see two plots. The first one is the residual plot. Okay. This looks bad, right? Not good at all. So we can clearly see that there's a pattern, and usually this pattern right here is less indicating that there are, say, like a correlation, but more indicating that we're not modeling the regression function properly. Okay? And also looking, let's go ahead and look at the second plot, normality. Right, it's not the greatest, right? This tail behavior is not very good. The rest of this is kind of right? So certainly not the best, certainly not the worst either, but just based on that first plot alone, we certainly know that our model's terrible. But if we were paying attention, right, this was our plot of x versus y to begin with, right? We noticed that there was this curvature to begin with, okay? So, well, we can even see what the model looks like. How about, right, AB line right here? Just toss that on there, right? This is our regression model. Does this look like it fits very well? No, of course it doesn't, right? Because there's a curve. And that's exactly what we saw when we did the residual plot, is that there was a curve. And so in this case, we can kind of clearly see, well, there's only a single variable, but we can also clearly see that there appears to be some higher order, like a quadratic relationship between x and y. Okay? So let's go ahead and account for that. So how about, I'll just put it like this, days.sq, days squared, is equal to days, and you can do it like this, days squared, or you could put days times days, really doesn't matter, okay? So basically I'm defining a days squared variable. Unfortunately, I have to do this. It would be nice if I didn't have to. So I'm just going to tap up so that I don't have to type it in again. I'm going to be kind of lazy. Okay, I found it, right? This was my regression model. I'll put reg.model2 though, just to distinguish it. And I need to put, so I have y versus x, and I need to put plus x squared, right, which is days squared. Unfortunately, I can't just put plus days times days. Unfortunately, that doesn't work. Okay? So, summary reg.model. Okay, notice I did something wrong, right? And right, I call it's reg.model2. So maybe to prevent errors, you should call it the same thing. I don't know. But, well, clearly I can see right there, where's my days squared? Well, oh, it's not here, right? Because it's reg.model2. So what do we have? We can clearly see that right here, based on this p-value alone, it looks like the squared term is needed, right? And we can basically just look at the graph and see that it's needed. But anyway, we have evidence based on this p-value that it's needed. And one other thing to notice, now when we have days and a squared component of days, we now account for about 74% of the variability in the number of new cases, right? So we accounted for 20% more of the variability, okay? So obviously, again, the higher that is, the better. Doesn't guarantee that the model's good, but the higher the better. So we can clearly see more evidence that this squared component is needed, because now we're starting to get into the better range of how good the model is. Right, we're accounting for 74% of the variability in the number of new cases now simply based on days and its squared component, but really it's only one variable, right, days. Okay. And so just to see, right, this is our, I'll do this so we can compare Windows. Okay. Plot days and new cases. Okay. And now I'm going to do AB line. I'll just make sure to put reg.model2. That's okay. Well, remember I did do this in a previous example. I can't use the AB line function. I have to put a curve. So that graph isn't right. It's not really worth the time. Anyway, if I look at now what this regression model looks like, it's going to be much more of a curve, right? And it's going to fit the data points much better than this line. Okay. So, of course, all of this interpretation was right for our simple linear regression model, right? All that was right. However, we saw at the end, right, so probably something we should check toward the beginning before we go through and interpret everything, is the fact that, well, this model wasn't good, right? We needed this squared component. So none of this is kind of right anymore. Okay, so what our model looks like now is the number of new cases is equal to, where's my model? Ugh, e to the 0, why are you putting it like that? (3.16) minus 0.04 times days plus 0.0002 times days squared. Okay? So this is our new model. And so now, again, I still just have days. And that gives me new cases. So let's see. And so it should be the same. Now we'll do a prediction interval for reg.model2. I guess you have to put days squared too. Anyway, I won't give you a. I'd have to figure out how to put that in. If I give you a prediction interval, it's either going to be for simple linear regression or potentially a higher order regression, but where they're just the baseline components like x1, x2, x3. Okay, fairly simple. Okay, so don't worry about if there's a squared component, I won't ask you about the prediction intervals. Okay. So the confidence intervals, okay, we get these, and right, these are now the confidence intervals that matter. However, right now, now that we have this squared term, we don't have nice interpretations anymore, right? There is no increasing days by 1 unit like we had here, right? This was very nice, but now, right, when we increase days by 1, well, this is squared days, so this squared days matters where x is, right? Whereas if we just had x, it doesn't matter whether you increase x from 0 to 1 or 90 to 91, but when we have a squared days, it does matter because now, right, there's a difference between squaring 0 and squaring 90, right? So this matters, and so the interpretations go out the window. Okay. You could still interpret the intercept, but that's about it. Okay. Let's see though. Did we fix our model? Remember last time we just looked at this plot. We had this big curve here in the residual plot, indicating that the model was terrible. Okay. So we're still seeing a squared a component, surprisingly, reg.model 2. Interesting. Okay, I'm kind of surprised that this is as bad as it is, to be honest. Um, that's interesting. Okay, so based on this plot, so it really didn't seem to help all that much. Okay, so um, there's still clearly a problem here, and see there there are lots of problems that you can encounter and lots of methods that you can use to try to fix them, but really we only kind of skim the surface a little bit as far as whether you might need to add a squared term or you might need to add an interaction, but there's lots of different techniques. We might need to um, take say the log of y or something like that. We might need to transform one of the variables or use some other technique to try to fix this, but this is clearly still not very good. Okay. And again, this is less talking about the assumptions, right? What assumptions is this plot indicating? It indicates to us whether the terms are correlated, and usually you're just going to kind of see up and down patterns. So um, it's unlikely for that. Is it indicating non-constant error variance? Well, um, maybe. Um, it's kind of hard to say. It does look like there's a lot of spread here, but maybe not as much spread here. So it's kind of hard to tell with such few data points, but maybe the variance is much higher here than here. So maybe that we do have non-constant variance here. That's actually possible. And of course, just this pattern here, just not a good indicator that we're modeling the data properly. Okay. Normality looks good though. Okay, remember the plot before looked much worse than this. This looks good. But based on those plots, I would still say that we probably need to use some other technique in order to fix the problem. Okay, because this is still not, this should be better. Okay, and so if this is actually an instance of non-constant error variance, which maybe it is, we can see that there are still 5 points here, but they're all clumped, and there's about 5 or 6 points here, and they're all spread out. So maybe it's a little maybe harder to tell because we don't have very many data points, but maybe if this is non-constant error variance, there are certain techniques like weighted least squares, other things that we can do, but as far as what I would want you to tell me, right, we've already added the squared component, and beyond that, I would just expect you to say, well, there's still something going on here, right? And everything is not a-okay. Okay. Okay, so we've talked about the correlation, we've talked about prediction and confidence intervals, and we've talked about the assumptions. And so I'm going to have one more example where we discuss the interaction term.